Okay, I've been calling what we've been doing so far in chemistry early chemistry. Um, we saw last time I finished what I wanted to say about Lavoisier, and Lavoisier was really the father of modern chemistry. I mean, we saw chemistry transformed into a real science by Lavoisier, and I described to you how Lavoisier made an objective distinction between elements and compounds. Right? Before there was a lot of speculation. People talked about the elements being earth, water, air, fire, and then certain people had suggested mercury and salt and sulfur, but the Lavoisier, I mean, it was speculation before Lavoisier's time. And I mean, how did Lavoisier distinguish between elements and compounds? Evan?
Well, he said that if something is an element, then you can't break it down by any chemical process.
Right, and ultimately, what was his criteria for breaking down? I mean, how did he? What measurements did he take to make to?
The weight.
Yeah, everything was done by was quantitative in Lavoisier. Every time he did a chemical experiment, he weighed the chemicals before they reacted, and he weighed them after they reacted. And so he has this measurable, quantitative, objective criteria for distinguishing elements and compounds. If something is a compound, then you can break it down into two or more elements that, when you weigh them up, weigh the same thing as the original compound. So, by the when I mentioned to you that Lavoisier's major book was published in, anybody know the year? Roughly. Was it the 600s? Was it the 1689? 1687 was what the year of what famous book? Newton's Principia. Okay, so Lavoisier is obviously after that. It's about 100 years after that. That's a good way to remember it. I mean, the modern physics really was born with Newton's Principia, right? I mean, that's when it came to maturity, the science of physics. That's in 1687. Well, chemistry is just about 100 years later. It's in 1789. Okay, now, once chemists had this objective way to decide between elements and compounds, and they had the right method to follow, I mean, chemistry became a real experimental science, the way physics was with Newton Lavoisier did that. Well, chemistry people have been doing chemistry and messing around in furnaces with chemical reactions for hundreds of years. I mean, since in the Middle Ages, this was popular. But they hadn't been getting anywhere. As soon as they had an objective language and an objective method, and they knew how to approach the subject, just like people knew how to approach physics after Newton, progress just exploded. I mean, in the next few decades after Lavoisier, more progress was made in chemistry than had been made in the previous 5 centuries. So you can see that once scientists are put on the right track, then and there was nothing impeding their progress, then the subject just exploded. let's dive into, I don't know, let's just call this post-Lavoisier chemistry. It's a bad name, but I hadn't thought about what I was going to call this lecture. That's as good as any I can come up with. And the the first, well, actually, before I dive into the main topic, I wanted to tell you about. I want to tell you about one important experiment that was done. Remember, I told you last time that the main way that Lavoisier had for deciding that something was a compound rather than an element was you break it down into its elements, right? Well, in the case of the proof that water was a compound and not an element, you know, the Greeks and everyone since the Greeks had always assumed that water was a pure element. Okay, well, I told you about the experiments that showed that water was actually a compound. Who remembers that? Daniel? Yeah, it's hydrogen and oxygen, but how was it done? How did they show that?
What I think it was Cavendish did.
Yeah.
He took 2 volumes of hydrogen and 1 volume of oxygen, and he tried to spark it to see if it was the pure air that everybody was looking for, the fire air.
Right.
Or water instead.
Yeah, right, exactly. But what he did was he got hydrogen gas by taking a metal, say metal filings, and pouring acid on them, and that generates, you know, a hydrogen gas will bubble up from that. Okay, and so he captures the hydrogen gas, and then he can take a rusted metal, okay, and heat it up, okay, and he can get oxygen gas from that. And then when he puts the two together and sparks them with an electrical spark, they ignite, and he gets water out of it. Okay, so what he did was he took 2 elements, hydrogen and oxygen, and got them to combine and got water. Okay, now, given that water is a compound of hydrogen and oxygen, we should be able to break it apart, right, and get the hydrogen and oxygen back. Now, but nobody had done that. I mean, Lavoisier never did that. Cavendish never did that. And it wasn't known how to do that. Well, somebody figured out how to do it right after Volta invented the battery. This was very shortly after Volta published his paper on the electric battery. A couple of scientists in England actually managed to decompose water into hydrogen and oxygen. Here's how they did it. So the first experiment that I want to tell you about this morning is, let me see, call this the decomposition of water by electrolysis. And it was done by a couple of scientists named Nicholson and Carlisle. in 1800. Now, what they did, and I'm not actually too certain what gave them this idea, but they took a battery. So they, I mean, the battery, one of the batteries that Volta described was a series of zinc and silver plates, right, separated by a salt or acid solution. So they took one of these silver and zinc batteries, and so you got a battery here, and say this is the silver side, say, and this is the zinc side. The silver is minus, the zinc is the plus terminal. And they took a brass wire at first, and they just led the ends of the wire into a container of water. So you got a little, say a cup of water or something here, and you just lead the brass wires into it. Now, what they found was that the wire that was hooked up to the zinc plate here would get tarnished. It would turn black. Okay. And then this other wire, the one that was hooked up to the silver, they saw bubbles forming around that wire, bubbling up from the water here. And so that led them to wonder, well, obviously some gas is being formed here. And when they captured it and analyzed it, they figured out that it was hydrogen. Okay, so now that next, what they decided to do was to use a different metal rather than brass, something that doesn't tarnish so easily. Okay, so they picked for their next experiment, they pick platinum. Okay, so platinum. So they use a platinum wire, and so that's okay. So that's their first experiment where they noticed the bubbles. Now, variation on that experiment. They switched to platinum wire. And now what they see is bubbles coming up from both wires. And they place containers over both wires to collect the gases. And lo and behold, it turns out, as I'm sure you can guess at this point, I've given you enough hints, that the gas bubbling from one of the wires turns out to be oxygen, and the gas bubbling at the other wire turns out to be hydrogen. Now, when they carefully measured the volume of the two gases, what do you think they found? Daniel?
It was twice as much hydrogen as oxygen.
Yep. And what do you think happened to the water level here? Evan?
It decreased by the volume of the gas.
Well, I mean, it decreased. Now, of course, this was a liquid, and then what they're collecting is gases. So the relationship of those volumes, a small decrease in the liquid creates a lot of gas. But the quantitative data that came out of this experiment was, I mean, yes, the water level went down, and as it went down, twice the volume of hydrogen was produced as oxygen. But this was a clear case of, obviously what was going on here was they were breaking the water down into its elements, into hydrogen and oxygen. So this was the very first proof of analysis of water. Cavendish had synthesized water from hydrogen and oxygen, and now they could go the other way around, and they could actually break water down into hydrogen and oxygen. Yeah.
Is this process used for? Would this process be used for other compounds too?
Oh yeah. It turns out that this was one of the reasons the battery was such an important invention. Was as soon as Nicholson and Carlisle did this, chemists realized, well, the battery gives us another tool in chemical analysis now. And this process became known as electrolysis. That somehow you could stimulate, with electricity, you can stimulate chemical reactions. And you can get, chemical reactions that won't take place, without the electricity. I mean, if you just stick these wires in the water and you don't have this battery connected, you break this connection. Well, nothing happens here. Then you hook up the battery and you start seeing the bubbles. Daniel.
I know they don't know, but why is that you need them? Because I know we know today. Why does that happen through electricity?
I'm going to explain that eventually, but I'm not going to give you the explanation right now because, see, at this stage, the scientists themselves couldn't possibly figure this out because they didn't have the knowledge they needed. And I haven't given you that knowledge, really. But it has to do, this whole section on chemistry, I've already told you, is leading up to the proof that matter is atoms. And then eventually we'll get to, I'll tell you some experiments that will show you the actual structure of those atoms. And once scientists finally got to that stage, which was in the late 1800s, so it took most of the 19th century to figure this stuff out. And then at the end of the 19th century, they could look back and figure out what was actually happening in electrolysis. And I can sort of give it away now. I mean, water is not just a compound that's 2 parts hydrogen and 1 part oxygen. It's hydrogen and oxygen are, in fact, atoms that come together into molecules, and those molecules have certain electrical properties, and they can be broken apart by electrical forces. And I'll tell you in more detail how that works when we get to the end. But at this point, all scientists knew was that it did work. They didn't know why, but clearly they did know something. I mean, this whole phenomenon of electrolysis told them that there was a close connection between chemistry and electricity. Okay, and they did not know that before, and it was Volta's battery that opened up that started the connection between those two subjects. Okay, so Lavoisier had said ideally, if you wanted to prove that a compound was made of these 2 other things that were its elements, that you should be able to go both ways, that you should be able to break the compound down into the elements and then combine the elements to get the compound back. Well, at this point, they can do that with water. Okay, well, the next guy I want to tell you about is a French chemist named Joseph Proust. I think it's pronounced Proust. But he came up with he announced a very important law of chemistry in 1799. So let me, his law is called the law of definite proportions. Which sounds fancy, but is actually pretty easy. I don't even think it will surprise you very much, but nobody said it and announced it as a universal law of chemistry until Proust did it in 1799. And we've already seen examples of this law. I mean, let's just well, let me start giving you the evidence, and then you can tell me what the law is. I think, well, I told you that in the Cavendish experiment, one of the things that Cavendish and Lavoisier had done in combining hydrogen and oxygen to get water is that they had weighed the 2 gases. And they had discovered that if you had 1 gram, say, of hydrogen plus 8 grams of oxygen, that would combine to give you 9 grams of water. Now, let's say that you have 2 grams of hydrogen here, but you only have the 8 grams of oxygen. Okay, so Cavendish combines them and he sparks it. What will happen? Dan.
You'll still get 9 grams of water, but you'll have 1 gram of hydrogen extra.
Exactly. How did you know that?
I just took a random guess.
That's a good guess, though. Now, if you think about it, though, that's an important fact, isn't it? Because, why couldn't you just make a kind of water that maybe tastes a little different? It was a little richer in hydrogen. So you could go to the store. It's like at the store they sell milk, right? And you can get it, fully fat milk, or 2% milk, or 1% milk. And they taste a little different, right? I mean, 2% fat and 1% fat. Well, why can't you go to the store and where they sell the bottled water, hydrogen-enriched water, or oxygen-enriched water, has a little extra in it. Well, it turns out you can't do it, no matter how hard you may try. 1 gram of hydrogen will always combine with 8 grams of oxygen to give you that 9 grams of water. If you have extra oxygen or extra hydrogen, it just doesn't react and you have it left over. Okay. Let's take another example. 3 grams of carbon will combine with our 8 grams of oxygen to get 11 grams of, any guesses? Yeah.
Fixed air carbon dioxide.
Yep. Yeah, Black's fixed air. Now, same thing. If you have, under these circumstances where you can create this fixed air, if you have extra oxygen or extra carbon, it just doesn't react, and it's left over. This is the amount of carbon that will react with that amount of oxygen to produce this gas, this fixed air. It always reacts in that proportion by weight. Now, I'll give you one more example. This is an example that Proust actually discovered. He was doing experiments where he was taking various experiments where he took carbon and combined it with, it's not carbon, copper, and oxygenated it, combined it with oxygen under different circumstances. And he found that he could actually generate 2 different compounds of copper and oxygen. So in one case, he found that 4 grams of copper combined with 1 gram of oxygen to produce a 5 grams of, let's say, a black compound. And then he also found that there was another compound of copper and oxygen that could be produced, only in this case, 8 grams of copper combined with 1 gram of oxygen, and gave a kind of reddish-brown ore. This compound, sorry. Okay, so he could have 4 grams of copper and 1 gram of oxygen to produce this black compound, or he could have twice as much copper that would combine with the same amount of oxygen to produce this different looking red-brown ore that had different properties. Yeah. Yeah, I mean it's like a rusted metal. Yeah. Excuse me? Yeah, in both cases, except they look different and they have different, different properties. They would have like different melting points, for instance. Okay, so now there were cases where it seemed like the same substance, like tin or copper, would combine with varying amounts of, say, oxygen or sulfur. Okay, and this seemed to fly in the face of what chemists were finding, with, for instance, water, where hydrogen and oxygen were always combining in the same proportions by weight. Well, what Proust proved was that any time you had one of these cases where it seemed like, for instance, copper would combine with varying amounts of oxygen, what was happening, can you guess? What's happening for instance, if you don't have an exactly like a 4-to-1 ratio of the weight, or exactly an 8-to-1 ratio of the weight every time. Let's say you do an experiment and the ratio of weight of oxygen that reacted with the carbon, the weights are in a ratio of 6.2 to 1 or something like that, rather than the 4 to 1 or the 8 to 1. Can you think of what might cause that? Well, you're not producing a pure substance, is what Proust showed. What you've got in that case is a mixture of these two different compounds. Okay, so any time that the ratio of the weights didn't come out as expected, Proust was able to show in a number of cases that you didn't have a pure compound in those cases, that it could be split up into 2 or more pure compounds. And that if you did have a pure compound, then every sample of that compound would always be produced by the exact same ratio of weights of the elements. Okay, so that is exactly what he announced as his law. So let's write down this law of definite proportions. different samples of a compound always contain the same elements in the same proportions by mass. So that's just what I was saying about water. I mean, every sample of water that you have will have an 8-to-1 ratio of oxygen to hydrogen by weight. And every other chemical compound is exactly like that. It's every sample of fixed air, always has this 8-to-3 ratio of oxygen to carbon by weight. Okay, well, you can see that's a handy thing for chemists to know, right? It's certainly, if you think that you have water and you analyze it and you don't get that weight ratio, then there's something wrong with your water. You didn't have pure water. So, like I say, in addition to the examples that I gave you, Proust actually did a whole bunch of experiments with tin and iron, combining them with oxygen and sulfur and so on. And so he had a pretty strong case for this law. Now, there were chemists at the time that argued with him and tried to come up with counterexamples. And what happened in each one of those cases was, eventually the counterexample would always be shown not to be a pure compound, to be a mixture of two different compounds. Okay. All right, well, that sets things up for our next guy. And this is the guy who is often referred to as the father of the atomic theory. Okay, so, and his name is John Dalton. Let's see, okay,
Is this number 3?
Yeah, you can call him number 3. As far as importance goes, he's number 1 of the guys I'm talking about this morning. And this, he came up with the first hard scientific evidence that matter was made of atoms. And it is, well, his atomic theory was based on a law of chemistry that he discovered. And his law of chemistry is called the law of multiple proportions. Which he discovered in 1803. Now, this was when, people had been talking about atoms since who? Yeah, Ben.
It's a different question.
Oh, you have a different question? Oh, okay, I'll take it.
How come when you split apart atoms,
Yeah.
they blow up?
Oh, that's a nuclear physics question, which maybe at the end of the course I'll tell you a little bit about that. But it's we have a long way to go to get there, because not only don't they know about, I mean, you've probably heard, all of you have probably heard that not only that matter is made of atoms, but that atoms have a little heavy nucleus and there's these electrons that go around it. I'm sure you've all heard that, but it actually turns out to be true. But we're trying to get there through the evidence, and these guys don't have a clue about that. And we'll see that Dalton actually had some wrong ideas about what atoms were that had to be straightened out later. But this was, people have been talking about atoms since ancient Greece, right? Do you guys remember Daniel?
Democritus?
Yeah, Democritus was the, well, I mean, he wasn't the first atomist, but he was the first one that actually wrote something that became influential. And I mean, this was 400 BC, and so more than 2,000 years went by after that, and still nobody had scientific evidence for the idea. I mean, it was just an idea based on loose arguments with no real evidence supporting it until Dalton, really.
Wasn't that the case with all the other ones too?
What?
So that they had
With-
no true pure evidence, like to prove their theories, and so why was
Which theories do you have in mind? You mean in ancient Greece?
well, not only ancient Greece but throughout time there was the thought of fire, air,
Yeah. Okay, right.
and other ones that were always regarded as a higher possibility over that. Why was that when they just had as much evidence as the others?
Oh, well, I mean, there were a lot of things that were known I mean, even the Greeks grasped some true and important things about physics. I mean, contrast their idea of atomism with their some of the things they said about electricity and magnetism, for instance. I mean, they said, well, they identified that iron was the only magnetic substance, and they showed some certain properties of magnets that didn't apply to electricity and vice versa. So, I mean, they said some true things, but those were based on observations, right? Whereas this in Greece was, the atomist idea was a bolt out of the blue. Now is when it starts becoming based on observations, and I'll tell you about those observations in this afternoon's class. So I think we're done for this morning.